Yeah.
About the exam, so there was one question, it asked something about unbonded electrons. Did they mean lone pairs? Because
I was gonna check on that one.
we've never, even in a homework, we've never
It,
used
it,
that.
it was worded with, I forgot to check on that one.
Yeah, I was so confused, and I thought it was lone pairs, and I chose the one that the only one that had a couple lone pairs. I think he asked 2 or something, and it was so wrong, so
Yeah. It used different language than I used in class, didn't it? And so I'll tell you what, the language we used in class was lone pairs, right? So if you put the number of lone pairs that there were, and if that was correct, I will give it to you. Fair enough?
Yeah.
So, yes. Man, a lot of mistakes. Any other mistakes? Who's going to email me to remind me?
I'll do it.
Thank you. But yeah, there's 2 of those. I'll get them both. Okay? So hopefully that even brings the average up higher, right? I'm good with that. Anything else? Okay. Today we are going to talk about different types of chemical reactions in general, balancing chemical reactions, or chemical equations. So let's go and get started. Okay, so let's start with maybe a chemical reaction we did with sodium and water, right? Sodium plus water gives us sodium hydroxide plus H2 gas. Now, a lot of times, or in fact always, we need to include what state of matter it is. So sodium is what?
It's a solid.
That's a solid. Water is a liquid. And once they react, we got a solid into water. It still looks like water, doesn't it? But all we have is this and this. So what we say this is AQ. Anybody know what that stands for?
Aqueous solution.
Aqueous solution means it's a water solution. So it's a water solution where sodium hydroxide is dissolved in it, okay? And then hydrogen gas is a gas, right? So this is an example of a chemical reaction. The compounds or elements or substances on the left side we call the reactants. Does that make sense in everybody's mind why we call it reactants? Because the sodium reacts with the water. What do we call the guys on the right side?
The products.
The products, because they are produced after the reaction. Good? Any questions about just general chemical reactions? Okay. Now, if we look at this equation, or this reaction, this is an ingredient list. That's all it is. Can we make fettuccine Alfredo with an ingredient list? Can we? Trial and error, we could. But what do we really need to make fettuccine Alfredo? A recipe, right? So let's change the ingredient list to a recipe. What do? We got to know how much of each, right? Okay. So I'm going to write this again, and I'm going to omit the states of matter for now just to keep it simplified. But I just showed this one because it shows all of them that we'll see in this class. So maybe I should write down what they are. This is solid This is liquid. This is aqueous solution, or I'll put aqueous here, or water solution. And this is a gas. Okay. So sodium plus H2O plus water gives us sodium hydroxide and hydrogen gas. Now let's see. Does anything look wrong with this thing? Yeah.
It's not balanced.
What do you mean not balanced?
Like, you need to have the equal amount of products or whatever.
Okay, so we look at sodium. There's one sodium here, there's one sodium here. So far, so good, right? There's two hydrogens here, and there's 1, 2, 3 on this side. You see that? That's why it's just an ingredient list. Okay? So if we balance it, it turns into the recipe. Recipe not for fettuccine alfredo, but for whatever reaction we're dealing with, right? To make sodium hydroxide and hydrogen gas. Are we good? So let's see. Maybe we should, I don't know, put a 3 right there. That'd be good? Why not?
Because you're changing the identity of the.
Yeah, this is no longer water, right? So we cannot change the prefixes when we do this. Cannot. Never, ever. Instead, we're going to add coefficients. You guys know what coefficients are? So if we have 3x plus 2, what's the coefficient of x? 3. The number in front is called the coefficient. Are we good? Oh, we're not going to do math, don't worry. Okay. Well, we probably will, but it's just counting. You guys good counters?
Yeah.
Oh, good.
You can count on it.
Okay. All right, so we're going to just put prefixes in front. So let's see. Here's a good way to do this right at first. On the left side, what elements do we have? Sodium, hydrogen, and oxygen. Good? On the right side, we better have the same elements. If we don't, something is wrong. If it calls for flour and you end up with something without flour, you did something wrong, right? Okay. So we also have sodium, hydrogen, and oxygen. Now let's just count them. So 1 sodium on the left side, 1 sodium on the right. So far, so good. Hydrogens, we have 2 on the left, and we have 1 here, 2 right there. That makes 3. Good? And oxygen, we have 1 on the left, 1 on the right. So everything's good except for that darn hydrogen, right? Okay, we got to put coefficients in front of what? Either here, here, or here. Or all of them, right? So we got to make it work. Now, ladies and gents, I'm going to show you some tips and tricks, but you don't have to know tips and tricks. You could just count these and make sure they're the same and just trial and error until it's done. Sometimes that trial and error makes you pull your hair out on the way. Because it's like, oh, come on, why? So these tips and tricks really help, but they aren't required. So you can write them on your reference sheet, but again, it's just counting, guys. Okay. So let's see. What should we do? Any ideas? What number should we put down and where? We have 2 right here. This side's always going to have what? How many? An even number. Do you see that? No matter what we put right there, it's always going to be even. Because it's that number, whatever it is, odd or even, multiply 2 is going to be an even number. You with me? Same with this one. No matter what we put there, it's always going to be even. But this one is always going to be odd. Well, it's not always going to be odd, but it's odd right now, right? So if this side's even, let's make this side even. Even plus an even makes an even, right? So let's make this one even. So what should we do?
Multiply it by
Put a
or
2. Multiply anything by 2 makes everything even, right? Okay. So that's a little quick trick. Okay. And I'll make a list of these tricks and kind of explain. I'm just going through this one just as an example. All right, so now let's recount. We have 1 sodium on the left and 2 sodiums on the right. So what do? Put a 2 over there. Okay, sodium's good now, right? And we're just going to go back and forth until we're good. Let me erase this X, because we don't need an X there. Okay, hydrogens, we have 2 on the left. Now we have 4 on the right. So what do we need? A 2 right there. And now we have 4 on the left as well. You with me? Okay. We have 2 oxygens on the left, and we have 2 oxygens on the right. Oh, done. We good? So that's just burning through it, the hard, just trial and error until you get it, right? So start with low numbers, guys. Don't just put a big, huge number out there. That just throws everything up. And besides, when we're done, it has to be simplified. It doesn't have to, but what happens if everything's multiplied by 2? You just doubled the recipe, didn't you? Okay? We don't need a doubled recipe. We just want the basic, simplest recipe. Why? Because we like simple, right? Do we understand the basic principle of balancing equations? Just to make sure that there's the same number of each element on each side. Because it has to be that way. If we start with so many atoms on one side and we react them, if we don't have the same number of atoms, we just destroyed matter, and we can't do that. There's a law that says we can't, right? You with me? Any questions so far? Should we try another one? Let's see. Yeah. Okay, we have C3H8, which is propane, plus oxygen gas, gives us CO2 plus H2O. So if we burn propane, we're having a barbecue, we burn propane, we're going to get carbon dioxide and water. That's the byproduct, right? Good? Where are we going to start?
On the paper.
Yeah, just start counting. Yeah. So elements, we got carbon, hydrogen, and oxygen. Now, ladies and gents, as you get good at this, you probably won't have to write all this stuff down. You could probably just count it over here. Okay. Need to change it, change it. But at first, it might make it helpful. Okay? So carbon, hydrogen, oxygen. How many carbons do we have on the left side? 3. Now, I'm not going to write it yet. I'm showing you how I would do this. Just so in case if you want to do it, you can. Okay? So I count 3 carbons on the left. How many on the right? Just 1. So that means we need what coefficient on the right? A 3. Oh, so now I have 3 and 3. Then I don't have to just erase and all this kind of stuff, right? Make sense? Okay. So now on the left, I have 8 hydrogens. How many do I have on the right?
2.
So what coefficient do I need on the right? A 4. 4 multiply 2. And remember, that 4 goes to the entire compound, not just the hydrogen. I didn't mention that last time, but do you understand that?
Distribution.
Yeah. It includes everything. It's like parentheses, okay? Without parentheses. So now we have 8 on the left and 8 on the right. So far, so good. Now, oxygens. Which side should we count first? Left side or right side?
Left.
Yeah, normally we start on the left, but why should we count the right first?
Because we added the coefficient.
Yeah, they're already balanced. So if we do everything right, we shouldn't have to change that one, right? We might, but okay, maybe not. So let's count them. We got how many right here? 3 multiply 2. Do you see that? Because we have 3 carbon dioxides, and every one carbon dioxide has 2 oxygens. You with me? That means, but we have 3 of them, so that means we have 6. Or 3 multiply 2, that's 6. You with me? 6 oxygens there. How many here? 4. So that's a total of 10. All right, so what coefficient has to be there? 5. 5 multiplied 2 is 10. Done. So, do you see you don't even have to write this? You do it the way that it helps in your brain, okay? And I'll do it the way that you want me to do it. Any questions? Now, also, is this simplified as much as best it could be? Simple as it could be? Yeah. So that's how we know we're done good. Let's give you some, do you want to do one more before we do tips and tricks? One more? Okay. Go ahead and try this one. And if you feel like you need to pull your hair out, just wait. I'll help you. Don't worry. Some of them are pretty straightforward, and some of them are just, But if you feel that way, all you have to do is erase everything. Start somewhere else. Start over. Good. You have a question? Yeah, what's up?
Have different coefficients?
What's that?
They can have a different coefficient, right?
Yeah.
Okay.
Yep. But in the end, they have to have the same number of atoms. Good? Just tell me when you're ready. Good? All right. Do you want me to go through it showing all the elements? Okay, so iron, chlorine. So there's only 2 different elements. That's nice. 1 iron of each, so that part looks good, right? Chlorines. 2 on one side, 3 on the other. So
You have to make it the same.
yeah, so what are we going to do?
Coefficient.
Find the least common multiple of 2 and 3?
6.
6. So What number goes there to make 6?
2,
2. What number goes here to make 6?
3.
So it looks like we just swapped them, right? Okay. And then, notice we're going to have to change this now, right? So what does that show us? It shows us our first trick. Start with the largest numbers, right? Because if we start with the little numbers and then have to change the big numbers, we're going to have to start over anyway, okay? So start with the big numbers. So we have 6 chlorines, and now we have 2 fluorines on this side, so we need a 2 right there. Now it's good. Good? All right, let's write our little tips and tricks here. I would put this just on a separate sheet or just somewhere where you can just go back to it each time until you just get these down, right? And again, you don't have to use these. You really don't. We messed up and we started at the one at the least, and we got it worked out anyway, right? It works. Just takes more eraser, right? No big deal. Okay, first one, and these aren't in, well, I kind of give them the way that I start them, but in the end, it doesn't matter. First one, start with largest numbers. Sometimes it doesn't matter, and sometimes it works better the other way. This is not set in stone, but in general, this is a good starting point. Okay. Another one that we did already, if we have even number on one side and odd amount or odd number on other side, then use least common multiple. You understand least common multiple? Smallest number both numbers go into evenly. Okay. Okay, if, am I going too fast? Okay. If one atom appears multiple times on one side, save it for last. And again, sometimes you have to do it the first, right? But in general, that's the best thing to follow. If an atom exists all alone, save it for last. Because generally it's a small number, right? But if that's the last one you do, it's the last one you change, it's not going to change anything else, right? And we'll go through these. Just kind of want to get them out of the way, get them down. if a polyatomic ion, or if a polyatomic exists on both sides, the same polyatomic ion, I should say, if the same polyatomic ion ion exists on both sides of the equation, you can treat it as a single component. Or as a single element, right? Single atom. So then you're counting several or a couple atoms at the same time. And again, you don't have to do this. If we start trying this and say, I don't like that, then don't use it, right? But I kind of like it. Doesn't mean you have to. And the last one, am I going too fast? Okay. If you can balance using fractions, then do. You'll just have to go back and multiply everything by the same small whole number, just to get rid of that fraction. You can't leave it as a fraction, but if you say, okay, if I could just have half of that, I'd be done, right? Then do it. Then multiply everything by what? 2 to get rid of that half, right? Because if you multiply everything by the same thing, then it's still balanced. Good? Yeah. Well, let's. It's actually common. Let's do it, shall we? Does everybody have these? Good? We want to take a picture, whatever. And again, you don't have to use these. You don't. You can just do it like we started, right? Just go at it and count them and change the coefficients until it works. And then if you have to, just make sure it's simplified when you're done. Good? Okay, so let's do one. Let's do butane C4H10. This is the stuff in cigarette lighters. Plus oxygen gas gives us carbon dioxide and water. All right. So we have carbon, hydrogen, and oxygen on both sides. Where should we start? Should we start with carbon, hydrogen, or oxygen?
Hydrogen.
Hydrogen? We could. Yeah. Why?
Because it's the largest.
That's the biggest number. In general, I start with the compound with the largest. You don't have to start with hydrogen. You start with the compound with the biggest number in it, and then just start from left to right. Either way. But yeah, we could start with hydrogen. Let's do it. Okay? So how many hydrogens do we have on the left? 10. How many do we have on the right?
2.
So what coefficient are we going to put on the right? A 5. So now we have 10 and 10. Good? Now let's use carbon, because we're going to finish this compound. Carbon has 4 on the left. How many on the right?
1.
Just 1. So what coefficient?
4.
A 4. So we got 4 and 4. And it's a good thing we're saving oxygen for last, right? Because it's everywhere. Almost everywhere. Appears twice on the right side. So what side should we count on the oxygen? And we're saving this oxygen for last because it's all by itself. Then we only have to change 1, right? So how many oxygens do we have on the right? It's already balanced out over there. Yeah. I was just making sure you're awake. Thank you. Yeah. Okay. So how many oxygens do we have for carbon dioxide?
13.
Or just for carbon dioxide we have
Just
8, right? And this side we have 5, and that's a total of 13, right? What times 2 is 13? 6.5, that's a fraction, right? Or you can use a decimal, no problem. But if we do 13 halves, then we know we have to multiply by what? I mean, if it's 0.5, most of you know you have to multiply by 2 anyway, right? Doesn't matter. But it's easy to see, okay, we need to get rid of that fraction. Multiply everything by 2. But yeah, right now, 13 halves times 2 is 13, so we got 13 on both sides. It's balanced, but it's not good enough. We cannot have a half a molecule, half an atom, half a whatever. So we got to multiply everything by 2. Put a 2 right there. We're going to change this to be 13, because 13 halves multiplied 2 is just 13. Good? Do we all understand this? If you don't, please let me know, okay? Going to change that to an 8, because 4 multiplied 2 is 8. 5 multiplied 2 is a 10. And it's still lowest, simplest numbers because of that 13, right? And it's still balanced because we multiplied everything by 2. Does that make sense? Yeah.
Wouldn't the left side of oxygen have 26?
Yeah, these numbers are changed, aren't they? Let's count them again. Let's count them just to make sure we did it right. You can always check it, guys. Always. On the test, double check it. Make sure if it's not correct, it's not correct. Check it. If it's not the same, I mean. Obviously, if it's not correct, it's not correct. So let's see. We have how many carbons on the left? 8. How many on the right? 8. Okay, so far so good. How many hydrogens on the left? 20. How many on the right? 20. So far so good. We have 8 times 2, that's 16, plus 10 times 1, that's 10. That's 26 oxygens. 13 times 2 is 26. It's still balanced.
Yeah, I was just wondering.
Yeah, you do not have to have this. That's not your answer. Your answer is right here. So if you get it balanced with a fraction, and then multiply everything, you have to get everything. If you miss one, yeah, it's not balanced anymore. But if you get everything, multiply everything by that same number, it's still going to be balanced. But yeah, double check if you're not certain. You can always do that, and it's free. Okay? Good?
You said that leaving it as a decimal would be fine too?
Yeah, you can't leave it as a decimal, but balance it as a decimal, right? So we could have said this is 6.5 instead, right? But then we still have to multiply everything by 2. 6.5 multiplied 2 is still 13, right? Does that make sense? Yeah, you cannot leave it as a fraction or a decimal. But you can balance it there, and then just multiply everything by small coefficient, or small whole number. Good? Any questions so far? All right, let's do another one. We have calcium hydroxide plus sulfuric acid, H2SO4, and we get calcium sulfate plus H2O. You see I have hydroxide on both, do we have hydroxide over here? It's hidden, so maybe we can't use that one. But we have sulfate on both sides. We can treat that as one unit. But we have other oxygens, so don't get confused. And if you think you're just going to get confused doing this way, then just break it up into atoms, elements, right? So, but here's what I do. You don't have to do this. I change this H2O to HOH. Is that still H2O? Yeah. And now I have hydroxide on both sides. Do you want to do it that way for this one, just to try it? Okay. Okay, so I'm going to write down all of my components. I have calcium, we have hydroxide, we have hydrogen, and we have sulfate. You with me? On the right side, we still have calcium, we have hydroxide, we have hydrogen, and we have sulfate. So let's count. Where should we start? What?
With the polyatomic ion?
That one right there. Why? Because it has 2. I guess we could have started over here. 2 is the biggest number. So probably either one, right? We can start here or here. Where do you want to start?
Well, we can start with the hydroxyl because the the sulfate group is 1 on both sides.
Yeah, it's 1. So that doesn't help anyway, right? So a lot of times we'll look at that, oh, I'm going to start here because it has a 4. But if we say that's just 1 unit, it's like parentheses, right? There's no parentheses, so it's just 1 of them. Good? So calcium is 1 apiece. Hydroxide, there's 2 over here, so what coefficient do we need on the right side? A 2, right? So now I have 2 hydroxides on each side. You with me? Okay. And then, well, since I changed this water, that gives me 2 hydrogens now, right? So I have 2 hydrogens on this side, and I have 2 hydrogens on that side. So that's good. And now we have 1 of each of those and 1 of those. That one wasn't too bad at all, was it? Should we do it without making that an HOH? Let's try it. And you can just write it over if you want. Excuse me. All right. All right, this time there's a lot of hydrogens, right? Or oxygens. Should we start with oxygen? You want to do it this way, or do you want to still use sulfate as 1? Just try it like this? Okay. Just to show you, still works. Calcium, oxygen, hydrogen, and sulfur. Okay. All right, where do you want to start? Oxygens? Let's see. There's one right there, there's one right there, there's one right there. They're everywhere. So that's one of our tips and tricks. If you see it multiple times on one side, save it for last. Okay? Otherwise, we change it over here, change it over there at work, then you have to change something else, and it just drives you nuts. Okay? So let's not do oxygen first. Hydrogen's also multiple places. But watch what happens. Calcium, calcium, 1 and 1, right? Sulfur and sulfur, 1 and 1. Ugh. We have to start with hydrogen and oxygen anyway, looks like, right? So sometimes we have to, can't get out of it. So do you want to just start with oxygen? Yeah, that's what I said. Okay. So oxygen, how many oxygens is right here in this compound? So this one right here. 2. How many in this one? 4. This one has 4. This one has 1. What does that tell you, guys? You need to put a 2 right here because it's 2, 4, 1, 4. So we need a 2 right there, right? So we put a 2 there, and now it's same, so it's got 6 on each side. But we just changed the hydrogen. That's okay because we didn't count the hydrogen anyway, right? Worked out. So now let's count the hydrogens. How many do we have right here? Right here. 4. On that side. How many here? 2. And how many here? 2 and 2 make 4. Done. You see, it balances out the same way, regardless. There's just less things to count the other way. But your call. So maybe if there's a water here and you don't see the OH, then, and you don't have to use both of them. We could have said oxygen, hydrogen, calcium, and SO4 as one component. That's okay. You can mix and match. But do it the way that makes most sense in your head. This one wasn't too bad either way. Good? Did we go over all of our tips? Start the largest. We use that. Even number on one side, odd number on the other side. Use least common multiple. We tried that, right? Multiple times, leave that for last. If it exists alone, leave it for last. You did both of those. Yeah, we pretty much gave you something from all those steps. Pull this worksheet out and let's try some. Because we're not going to ever get good at it until we do them and do them and do them. Hold on. Did I? No. Okay, I didn't give you the wrong one. So on the worksheet, it says, you got a ton of them, right? And if you guys feel like you want to do one more together, we can. Just pick one of those.
Can we do, on the second column, it looks like it's spelled nano, N-A-N-O-3.
Yeah. All right, so we got, what's that? If you can tell me what that's called, we'll do it.
Sodium nitrous oxide?
No.
Sodium is an ionic compound. It would be.
That means the rest of it is a polyatomic ion, right?
Oh, right, that's nitrate, so it's
Yeah.
sodium nitrate.
There you go. Sorry, I didn't mean to put you on the spot, but
It's good.
we got to be That's why we learn this, so that we can know how to name these things, okay? Still got to be able to do that for the rest of the semester. And we get sodium nitrite. Yeah, this one's, I think, seems pretty, I think it was this one, maybe not. Maybe it's a different one than I was thinking of. All right. Where do you want to start?
Well, you can start with, on the left we have 3 oxygen, but on the right we've got 4 oxygen.
Okay. So you want to start with oxygen? Is that what you want to start with?
I mean, I know,
I would leave that one for last, and here's why. Oxygen appears multiple times on one side, and it's by itself on one side.
yes.
Save that one for last. It's going to take away the headache or not give it to you in the first place.
So, I guess.
But we have to start with oxygen, don't we?
To,
Because everything else is all balanced. Okay. But let's save this one for last. Good? All right. So let's see. We have 3 on the left and 4 on the right. That's what you said, right? This is always going to be what? Even or odd? On the right side, it's always going to be even because it's always 2 and 2, right? This side's odd. How do we make it even? Put a 2 right there. Okay? So now let's save the, now we didn't do the oxygens yet, did we? It's still not balanced. Because now we have 6 on the left and we have 4 on the right. Let's save it for last now. We good? You don't have to, but let's just do. So now we have 2 sodiums on the left and how many on the right? 1, so we better put a 2 right there. So sodium is good. We have 2 nitrogens, it's still balanced, so okay. And well, we have, it works out anyway. I guess we're done. 6 and 6, right? Because we had to put that 2 on the sodium. Now try it without doing that way. Try doing the oxygen first all the way. Maybe it's the same. I don't know. Some of them doesn't matter. Some of them, it really makes a difference. Okay? So again, if you forget the tips and tricks, no big deal. You can still do it. Okay? Yeah.
How'd you get 6 for oxygen?
How'd I get 6 for oxygen? Here we go. So 2 times 3, that's 6.
Okay.
And over here you have 2 times 2, that's 4. And plus 2, that's 6. Good? Sorry, I didn't really count those. I just said, okay, we got that, right? Sorry about that. Any other questions? Should we take a few minutes to just practice these? And then if you come up with an issue, then we can face it together. Try the hardest ones first. Unless you're just still having a rough time doing this period, then start simple. That's okay. Good? need 7 right here? Oh, 'cause we have 1 right here. 1 plus what is 7? 6. Oh, so what number goes here to make this 6? What times 2 is 6? Do you get that? And now we have 7 on both sides. 6 here plus 1 right there. You get that? So just double check them every time. Count. So just remember the coefficients go to everything in that column. Everything. And remember the number is going to be to the right of whatever element it is. So that 2 goes to the O. That 2 goes to the O. That 6 goes to the H. And you did everything else right, so you can. I think you know that. Just remember for all of them, right? Okay, how we feeling? Do you want to do any more together? Which ones?
Could we do the C3H8 is the third one on the right column?
Yeah, let's do it. I think we did this one. You want to still do it? We can.
No, not if we already did it, I guess. Oh, yeah, I just didn't look at my notes on
No,
my
you're good.
page.
You want to pick another one?
If we do the first one on the left-hand side,
Yeah. So aluminum plus sulfuric acid gives us aluminum sulfate plus hydrogen gas. Do you want to treat sulfate as one unit or separate it all? There's no other oxygens, no other sulfurs, so it might be good to just, on this one, to just use sulfate as one unit, yeah? Since it's the same on both sides, right? So we got aluminum, hydrogen, and sulfate. But again, you don't have to. If you just hate that one, don't do it. All right, where are we going to start? What compound has the biggest numbers? That one has a 2 and a 3, right? Should we start somewhere else just to see what happens? No? Okay. So that's a pretty good starting point, right? To start with the biggest numbers. All right. So we have 2 aluminums on the right, 1 on the left. So what do we need? A 2 in front of aluminum, right? So now we got 2 on each side. So far, so good? We have 3 sulfates on the right. How many on the left? 4? Oh, just 1, no parenthesis, right? So what do we need on the front of H2SO4? A 3. 3 and 3. Are we good? Questions? Okay. And then hydrogen, we have 6 right there and only 2 right there. So what needs to go in front of that H? A 3. Done. If you want to make sure you did it right, let's just double check. Count them again. Good? Anything else before we move on? If you guys want to stretch a little bit, you can, whatever. Get up and move. All right, and again, the answers are on Canvas. Try those and then check. Okay? All right, let's move on. But really, we can do more if you need. Okay? All right, there are 3 different types of chemical reactions that we're going to deal with in this class. So let's kind of just give you an idea of each one of these. So the first type, so let's just, I guess, label this here. So 3 types of chemical reactions. Type 1, oxidation reduction reactions. Or sometimes called redox. Okay. And this kind is when elements either gain or lose electrons. And we'll go in a little bit deeper. I'm not sure if we'll get there tonight, either today or tomorrow, next time. Okay. And the ones that are generally, I mean, the easiest ones to tell are in ionic compounds, okay? Because we know ionic compounds will gain or lose electrons to become an ion, right? So let's start simple. Let's go Mg plus O2 gives us. Oh, I should have brought a bunch of stuff to show you all these, huh? I missed. Oh, I'm sorry. I should have brought all this stuff, but I didn't. And I can't do it next time because we'll be done. I'm sorry. Okay. So magnesium and oxygen make, what does it make? Magnesium oxide, right? Have 2 elements that combine together to make magnesium oxide. What's the chemical formula for magnesium oxide? Can you guys do this? You should be able to do this. I don't know, let's see. We have to write Mg with the charge, right? What's the charge of magnesium if it becomes an ion for an ionic compound? 2 plus, right? It's in group 2, so it's 2 plus. Oxygen is? Oh, so what is it? We cross-charge. Don't actually do this, guys. Do it like I showed you how to do it until we're done with the semester. Do it this way. We cross charges, and we got Mg2O2. Is that good? No, why not?
Because it's an ion. So
Yeah, it's an ionic compound. It needs to be lowest whole number ratio. So it's a magnesium, MgO, right? Right. So you didn't have to do that for here. I was just kind of helping you know that you got to know how to do this, right? All right. And we can balance it, but let's see. Let's see what happens. What's the charge of just magnesium? It's 0, right? What's the charge of oxygen by itself? 0. Well, oxygen is by itself. It's with another oxygen, but that's okay. It's still neutral, right? Are we good? This is positive 2, and this is negative 2. Do you see what happens? Some of them gained, and some of them lost electrons. We can see that easily because it's just ionic compounds. So this is a redox reaction, or a oxidation reduction reaction.
Why is it 0 on the left side?
Because it's neutral. It's all by itself. Good question. So when atoms are all alone, they're not ions. Okay? They only become ions when there's going to be a chemical reaction, right? And so here they come together, and generally you have to have some kind of energy to get these things to bond, right? So we start with 0 and 0 because they're both neutral. How do we know that? How do we know oxygen's neutral? Because we're breathing it and we're not getting shocked, right? Yeah, it's neutral. Things are neutral in general until a chemical reaction occurs. Then they'll become ions, and then opposites attract, right? Okay. So which one gained electrons?
Or no, sorry.
Oxygen, because it becomes -2. More negative, more electrons, right? This one gained electrons, and this one lost electrons. So when that happens, you know this is an oxidation reduction reaction. Are we good? We'll go a little bit deeper later. Okay? But a good way to tell it's an oxidation reduction reaction is when you have this right here. This is a combination or synthesis reaction. That's what we call it. And the reason why we call it combination or synthesis, synthesis reaction is synthesis means to make, right? So we're taking two single elements and we're making a single compound. We combine them together, combination reaction, right? And we get this. If we ever have that type of reaction, this is oxidation reduction. We don't even have to worry about the ions, right? Yeah.
Would we need to balance this equation?
If we're going to use it, yes. Yeah. Right now, I'm just showing you the different types of reactions. But yeah, we will always need to balance our equation. Always. Not always, but always. My bad. Okay. All right. So that's one type of oxidation reduction reaction. Another one is the opposite. So this one, we started with single elements and we got a single compound. The next one, we start with a compound and it breaks up into its components. That's called a decomposition reaction. You don't have to know that, but that's why we call it decomposition, because it decomposes into its components, right? So combination combines together, forms one. Decomposition breaks apart, forms single elements, right? So that's another example of an oxidation reduction reaction. And another one, C4H10O, plus O2 gives us CO2 and water. Have we seen these a few times already? These are called combustion reactions. Why? Because this burns in the presence of oxygen. You have to have oxygen to burn, right? This is just a carbon-hydrogen compound. And when we burn a carbon-hydrogen compound in the presence of oxygen, we always get carbon dioxide and water. Wood. When we burn wood, we get carbon dioxide and water. When we burn gas, we get carbon dioxide and water. Every time. And we know this because this is the pollution we get, right? Okay.
So you said this is called what kind of?
A combustion reaction. Maybe I'll write that. So this is combustion. This is decomposition. You don't have to know these names, guys. But if it helps you to kind of recognize them, that's good. And this is combination. Slow down. Slow down. So all three of these are examples of oxidation reduction reactions. There is one more type, maybe I should show you. Aluminum plus, let's say, HCl gives us AlCl3 plus H2. So this one we call a single replacement reaction. Sorry. The reason we call it single, and you don't have to know single replacement reaction, you really don't. But we're going to be talking about double replacement reaction in a minute. And you will need to know that one. So here we have this aluminum comes over here, knocks the hydrogen off, and makes a compound with chlorine. And then hydrogen is all alone. Do you see how one atom is replaced? Just one. That's why we call it a single replacement. Good? So this is another example, because this is always going to be an ionic compound. Is that an ionic compound, HCl? It is, because it's an acid. Okay? We'll get there. Okay? That's an ionic compound. So if we have ionic compounds in our, well, not always. No, I'll just bag that. Okay? So those are 4 examples of oxidation reduction reactions. We'll learn more about those a little bit later. Either a little later today or next time. Any questions on oxidation reduction? Okay.
One question.
Yeah.
So, if there is a presence of ionic compounds, could you say that it's a redox reaction?
No, I was almost going to say that. Then I says, oh, not always. So no. So the question was, if there's presence of an ionic compound, right? Is it always oxidation reduction? No. Nope. How do you know it's oxidation reduction reaction? Because we have a transfer of electrons. That's really how you tell. So if we look at this right here, this one we start with, it's neutral, right? And now it's 3 plus. And this one is 1 minus. It still ends up with 1 minus, so no big deal. But this is 1 plus, ends up with 0. If we have one that gains electron, we have to have one that loses electrons. That's why we call it oxidation and reduction. One of them is oxidation, one of them is reduction. We'll talk later. Good? This one right here is hard to tell because there's no ionic compounds. We'll show that one later, okay? But if it's a combustion reaction, it's oxidation reduction. Good? Any other questions? Okay? Let's move on to precipitation reactions. All right, precipitation reaction is always a double replacement reaction. Okay, let me show you what a double replacement reaction is. Any ideas what it is? Where 2 things are being replaced, right? Instead of one like in single replacement. So for example, we have lead 2 nitrate, my bad, plus potassium iodide, and I'm going to start over here, mostly because I'm running out of room. You won't have to so much. Here we go. So put lead 2 nitrate. And it's an aqueous solution. Here's how you know it's precipitation. You have 2 aqueous solutions, and when we're done, we form a solid. Okay? Plus potassium iodide. I'm going to show you this one next time. Man, I wish I had brought all that stuff. I'm sorry. Would have made today a cooler class. So potassium iodide, also aqueous solution. What does aqueous mean?
Water.
Water solution. It means this salt is dissolved in water, right? Okay. And we're going to get, well, let's see, in a double replacement reaction, this guy kicks that guy off, and this guy comes over and kicks that guy off. They just swap partners. Sometimes this happens in real life. Okay. And we got PB. What's it going to be? If lead goes with iodine, what is the chemical formula going to be? Now, lead's one of those that kind of act like a transition metal, right? So we got to figure out, what's the charge of lead? Well, I called it lead 2. How do I know it's lead 2? Because nitrate is 1 minus, yeah? And there's 2 of them. That's -2. This is +2. So in this reaction, lead is always going to be lead 2. So it's lead 2 over here now. And it's mixing with iodine. So iodine is 1 minus because it's in group 7 or 17, right? Cross the charges and it turns into what? PbI2. You with me? Now it turns out this is a solid. Why? Because it does not dissolve in water. And I'll show you how you can tell that. Does not dissolve in water. And then we're left with, now potassium goes with nitrate. Potassium is a 1+ charge because it's in group 1, right? And nitrate is, we just figured out that was NO3 minus. It's on our polyatomic ion list. You got to know that. It's a 1-to-1 ratio, so we're going to get KNO3. This one's also aqueous. And I'll show you how to tell that. So that's a double replacement reaction. But this is how we know it's a precipitation reaction. Let's write that down, that word down. Precipitate. Anybody ever heard that before? On the weather station, right? Okay. It's a little bit different here, but when you hear it on the weather station, it's talking about raining, clouds, right? You have to have clouds to have rain, okay? So you got clouds. Well, and I don't have this, but I was going to show you, but I didn't, okay? If you mix 2 liquids, 2 aqueous solutions, they look like water, it's just salt water, right? And you form a solid out of it, that solid will just kind of settle down and flow, and it kind of looks like a cloud. But that's a precipitate. When a solid is formed from 2 aqueous solution. Oh, whoa, that was weird. Aqueous solutions. Good? Yeah.
For the lead and in the product, would we need to put the Roman numeral because we treat it like a transition metal?
Only in the name. Not in the chemical formula. We never use Roman numerals for the chemical formula. Just the name. So if we're naming this, yeah, it's called lead 2 iodide. Yep.
Okay.
Good question. We good? Any questions about precipitation reactions? Do we have ionic compounds here? Yeah, so that kind of answered our question. It's not an oxidation reduction reaction, and here's why. This lead is 2 plus, right? This lead is 2 plus. That didn't change. That didn't transfer electrons. This is -1. This is -1. That didn't change. This is +1. This is +1. That didn't change. This is -1. This is -1. We didn't transfer any electrons here. To create an ionic compound, we do transfer electrons, but we're not creating ionic compounds. We're just swapping partners. A little bit sketchy here, right? Good? Let's do one more. Is this a precipitation reaction? It is a double replacement reaction. Are all double replacement reactions precipitation reactions? No. How do we know this is not a precipitation reaction? No solid is formed. Okay? So this is not a precipitation reaction. Oh, should I not cross that out yet? Not precipitation. Because no solid is formed. Good? And we good? Any questions on precipitation reactions? The last type, and I think after this, I think we can call it a night. Okay? Is that too much? Did I give you too much information? Okay. Well, I could give you more. We're gonna dive deep into each one of these next time. Okay? We won't do that tonight. So the last type is acid-base reaction. So what's an acid? Anything with H plus is the cation. Hydrogen as the cation. This tells us it's an acid. And for now, we're going to keep it really simple. We'll go a little bit deeper in acids and bases in the last unit, chapter 10. Okay? But for now, let's just keep it simple. A base is an ionic compound with hydroxide in it. Okay? And that's how you tell if we have an acid-base reaction. If we have an acid and a base. You have to have both. Sometimes you can have a base without an acid. That's not an acid-base reaction. Good? So for example, we have iron 2 hydroxide. And I'm going to say one more thing before we get into this. An acid and a base, these are always aqueous solutions, always. If it's a solid, it's just a salt. Okay? Once you put that salt in water, it turns into an acid or a base. Okay? So it's always aqueous. This is also a double replacement reaction. So here's a quick and easy way, guys. If we'll get there. I'll slow down, sorry. So iron 2 hydroxide plus H2SO4, also called sulfuric acid. And if this is a double replacement reaction, can you predict what the products might be? Double replacement reactions, the cations swap places, right? And that, since this is iron 2, and again we can check, right? This is -1, this is -2, this is +2, so this is a +2 ion, because it's a transition metal. So it's going to be iron 2 with sulfate is SO4 2-. It's a 2-to-2 ratio. Simplifies to 1-to-1. FeSO4. And we'll have to determine what that is. But we'll just say it's aqueous for now. Plus, this H hooks up with the OH, and what do we get? Yeah. So this is also called a neutralization reaction. We take a strong acid, right here, a strong base, it completely neutralizes into salt and water. Good? So if we get a strong acid that if we get in our eyes, it's going to make us go blind. Strong base, same thing. They're both corrosive materials. And we mix them in the right proportions, we'll just get salt water. Isn't that crazy? Okay? So this is also called a neutralization reaction. For this unit, we're going to keep it simple, and that's all we're going to have if it's an acid-base reaction. Okay? And we have water and salt. That tells us it's a acid-base. But the main thing, guys, we have a base right here and an acid right here. You see that? Hydrogen is the cation, so that's an acid. Hydroxide is a base, so hydroxide in an ionic compound, that's the base. That's the base reaction. And for this unit, there are always going to be neutralization reactions. Good? Okay, so if we look at our worksheet, we could do section 2. Classify the following as oxidation reduction reactions, precipitation, or acid-base reactions. You want to give it a shot by yourself?
The 4th and the 6th ones are the same.
Then you better get it right. Otherwise, you got 2 of them wrong. Who can tell me what this first reaction is?
Acid base?
Acid base. We got an acid right here, base right there. It almost looks like that last one we gave you, right? And we get salt and water. Yeah. It's a double replacement reaction. This is acid base. Who's got the second one?
Precipitation.
Is it precipitation? What do you think, Jasmine?
I think it's oxidation.
Oxidation reduction reaction? Because
It doesn't form a solid?
it breaks, it's one compound and it breaks into two pieces, right? This is a decomposition reaction. And it's not a precipitation. In fact, ladies and gents, here's the easy way. You ready? If it's a double replacement reaction, it's either precipitation or acid base. If it's not, chances are it's oxidation. Good? But later because sometimes it's neither. But we'll get there. But for now, let's keep it simple, right? So it's not a double replacement reaction, so it's oxidation reduction. Or just redox, right? Does that make sense? Okay. What about the next one?
Precipitation.
Precipitation because it's two aqueous solutions forming a solid, right? And it is a double replacement reaction. Okay. Are we going too fast? What about the next one? Redox, because it's a combustion reaction, right? It's not a double replacement, so it's redox. Next one?
Acid base.
Acid base. We got the acid right here, base right there, and we make salt and water. Is this making sense to everybody? Am I doing all of your homework for you? Your practice, I mean, it's not homework. Well, it is, but it's not worth anything, except for practice. And we already did the next one. What about the last one? Precipitation, because we got a solid. It's a double replacement reaction. Good. Okay. Any questions? So get good at balancing equations and determining which type of reaction it is. That's just the first step. Okay? Okay. Have a fantastic night.